All right, so yesterday we looked at the derivative of the exponential function e to the x. And again, it was a special function because the derivative of e to the x is e to the x. Well, today what we're going to do is, again, look at an exponential function, but we're going to look at the general exponential function. All right, so it's given any exponential function where y is equal to b to the power of x. Well, then the derivative is equal to b to the power of x, but yet times ln b. And again, this is where a couple of things, where b is some number. Now, this ln b, it is also a number, and what ln is a logarithmic function, and it's a specific logarithmic function. When you have the logarithmic function on your calculator, or it just says log, it has a base of 10. And a log function can have any number of bases. But the log function that has the base of e, that's the ln function. So the ln function is just a special log function. All right, and also with this general exponential function is that, again, the chain rule applies. And so if you have y is equal to b to the power of f of x, then y prime is equal to b to the power of f of x, still times the ln of b, but yeah, then times the derivative of the exponent. So again, that is the chain rule for an exponential function. All right, so on that note, for example, it says find f prime of x for f of x is equal to 4x. So this is basically the simplest one we can come up with, to be honest with you. And so we have our derivative, f prime of x, and that's going to equal 4 to the power of x. So again, our b value here, our number is 4. And then we just go times ln 4. And there we go. All right, now most of your calculators, you can actually figure out ln 4 if we ever get there. Most calculators do have that on there. We might just do that. All right, example 2, again, just finding some derivatives. We have f of x is equal to 8 to the power of 3x plus 2. And so if we're finding our derivative, f prime of x, first thing we do is we have the original function, 8 to the power of 3x plus 2. And then we times it by the ln of the base, which in this case would be 8. So we have ln of 8. And then our derivative there is not just simple x. We do have a function, and so I take the derivative of 3x plus 2, and I end up with 3. And there's our derivative. Now I could rewrite this. Typically you might rearrange this so that it's f prime of x is equal to 3 times ln 8, and then times, I could also put it in brackets, 8 to the power of 3x plus 2. And there we go. All right, well, a little more complicated, a little more elaborate exponent on our next one, where we have f of x is equal to 7 to the power of x squared plus 4x minus 3. But again, fall in the same format here, where I have f prime of x is equal to our original function of 7 x squared plus 4x minus 3. Again, times the ln of 7. All right, then again, times the derivative of the exponent, which this time is going to be a little bit bigger. We're going to have 2x plus 4. And again, if I was to rearrange that, not like it matters, because again, when you're multiplying, it can be done in any order, but I could have f prime of x is equal to, probably go the number first, ln 7. Again, that's just a number. Ln is a special log function. Times our 2x plus 4. I guess we'll go with the polynomial. Least complicated to most advanced. And then finally, our exponential part of the equation, which is 7 to the power of x squared plus 4x minus 3. And there we go. All right, let's see. Try something a little bit different again, where we have example 4. Where now we have f of x is equal to 3x divided by x cubed. So we have a function divided by a function. So we're going to end up using the quotient rule here. I'll throw that in here. So we got the old quotient. I always struggle with spelling that word. Quotient. Oh, good. Quotient rule. All right, because again, we got a function divided by a function. And so if I find my f prime of x, again, with the quotient rule, you take the derivative of the numerator. So we're going to have 3x times ln 3 times the derivative of our denominator, which is x cubed, minus, all right, then we take the numerator, which is our 3 to the power of x here, and then we times it by the derivative of the denominator, which would be 3x squared. And then, of course, can't forget the denominator, which is just going to be x cubed, and then we have to square it. Now, I could simplify this function, I guess, particularly because sometimes we'll end up solving, say, for the denominator, or the numerator. And so I could look at it. We have a common factor there of 3 to the power of x. And then in brackets, I would have ln 3 times x cubed. Let's see, then minus 3x squared, it looks like. And then simplifying my denominator, when I have x cubed squared, again, power of a power. Grade 9 power rules here. We keep the base the same and we multiply our exponents. So we get x to the power of 6. And that's basically as simple as that derivative can be. All right, so that's a quotient rule. Next up is tying in yesterday's work. I have example 5 where we have f of x is equal to e to the power of 4x times 2 to the power of 5x. So again, we have a function times a function. And so this time I'm going to use the product rule. All right, which is it's very similar to the quotient rule. Even it's just a little bit easier, but this function is a little more advanced. All right, so let's see here, finding the derivative. Again, with the product rule, we take the derivative of the first term, which again is going to be e to the power of 4x times the derivative of the exponent, which is just a 4. All right, then times, let's see here, our second term, which is 2 to the power of 5x. Then we go plus, the second part is, well, we have our first term, e to the power of 4x. And then we times it by the derivative of our second term, which, again, it's a general exponential function. So we have 2 to the power of 5x times ln 2, and then times the derivative of the exponent, which is just a 5. There we go. I should put that ln in brackets because those 2 and those 5 do not multiply each other. It's ln 2 times 5. Big distinction there. There we go. I'm just going to leave that one alone. No sense of... Actually, I could common factor this because we have, in each term, in fact, we have a common factor of e to the power of 4x. And we also have a 2 to the power of 5x. And let's see, in our first term, all we need is a 4 there. And in our second term, we'd have 5 times ln 2. There we go. So that's a simplified version of that derivative. But again, just following our rules here, all the derivative rules that we've learned early on, and then applying them to our special derivatives of, well, e to the power of x, and then the general exponential function. All right, now let's see here. Let's look at a little application. Example 6, on January 1st, 1850, the population of Gold Rush Town was 50,000. The size of the population since then can be modeled by the function P of t is equal to 50,000 times 0.95 to the power of t, where t is the number of years since January 1st, 1850. All right. So in A, we have what was the population of Gold Rush Town on January 1st, 1900? Okay, so we want to know the population. So in A, what we're looking at here is we want to know the population. All right, at 1900. Now, this formula is the population since 1850. So in fact, 50 years have gone by. So we're just simply looking for P of 50, which would be 50,000 times our 0.95 to the power of 50. All right, and so let's see here. So I'm going to have 50,000. I take 0.95 to the power of 50, and I get 0.0769. All right, and then I multiply those two numbers, and in fact, in 1900, there was projected to be 3,847.25. So that's what we, this equation would be an exponential decay equation. Again, because our b value inside the brackets there is less than 1, so the population's decreasing, in my opinion. But I guess we'll get to that in B. Is that, in fact, at what rate was the population changing on January 1st, 1900? Was it increasing or decreasing? Well, I guess I gave that one away a little bit, in my opinion, but I guess it's kind of obvious. But in B, what we're looking for is we want the rate at which something's changing. So again, that is when we're looking for the derivative of our function. And again, at January 1st, 1900. All right, now the first thing we're going to have to do is actually find the derivative before we plug in 50 into our equation. All right, and so our derivative, p prime of t, is equal to, let's see, well, I got the 50,000. That's a constant. That's not going to change anything. But then I take the derivative of the 0.95t. Multiply. It is again a exponential function, so I have my 0.95t times the ln of 0.95, and then again times the derivative of our exponent, but the derivative of our exponent is just going to be a 1. All right, so again, I can put this ln 0.95 in brackets. All right, so let's see here. Now, time to substitute in. So I have my function, and again, I want my derivative after 50 years here, the rate at which it's changing. So I'm going to have 50,000 times 0.95 to the power of 50. And then that number is going to be multiplied by the ln of 0.95. All right, so just doing some calculations now. And again, you got to be able to find that ln button on your calculator. Now, if I take take 0.95 and times it by 50,000, you'll notice I actually did that up at the very top here in A. So I know that number. I'm going to have to calculate it. Put it in my calculator. It's 3,847.25. And again, did that part because the ln of 0.95, again, you got to be able to find that in your calculator, the big ln button. And I get a value of minus 0.0513. All right. So again, that's a little bit of practice here. You got to be able to find that calculator either on your calculator or on your cell phone or your graphing calculator. All right, and then I multiply those two numbers and I get minus, because I got a positive times a negative here, minus 197.34. Now, this is a word problem, so this actually means something. And again, I'm going to go back up to what the question's asking. At what rate, let's monitor catch up here, at what rate was the population changing on January 1st, 1900? Was it increasing or decreasing? Well, we got ourselves a negative value here, so I can tell you it is decreasing because it is a rate of change. And so, therefore, Gold Rush Town's population was decreasing at a rate of 197.34 people per year on January 1st, 1900. And there we go. So again, we actually found out how many people were in the town, and then at night at a certain specific time, and then we also found at the same time how many people on average were leaving at that particular time.